called Jordan-Wigner transformation. So what is this transformation? This transformation is the form. So you define operator like this. Let's call it 12 minus 1, which by definition is equal to product from j equals to 1, 12 minus 1 of sigma j z, sigma l x. And you define A to L, which is equal to the product j from 1 to L minus 1 of sigma j z, sigma l y. This is just definition. Okay? Why is this convenient? Because it's very easy to prove, and I leave this for exercise, that this operator A satisfies the following algebra. So the anticommutator between AL and AN, which means AL, AN plus AN, AL by definition. So this is equal to twice delta LN. Okay? So if you are familiar with the second quantization, then you can recognize that this satisfies the algebra of Majorana-Fermions. By the way, these are emission operators. Okay, so you have A dot L is equal to AL. So this is the algebra of spinless Majorana-Fermions. How are they connected with the usual fermions that you know? Well, simply you can, if you have a pair of Majorana-Fermions, okay, let's say that I give you two Majorana-Fermions that we call A and B that satisfy this algebra. So what I'm saying is that the commutator, so this operator such that A is equal to and AB is equal to 0 and it's also equal to BB. Okay? So I give you these two Majorana-Fermions. Then you can always construct a standard fermions in this way. We just consider linear combination A plus IB divided by 2 and A minus IB divided by 2 is the conjugate. So you define this operator B in this way. And then what you can check, so this means that this is B. What you can check is that B dot B is equal to 1, like for fermions. And you can also check that B dot squared is equal to 0. Why? B dot squared. So you can't have two fermions in the same state. B dot squared is equal to A plus IB times A plus IB. But A times A is equal to 1. Comes from here. So and B times B is equal to 1. So this becomes 1 minus 1 plus I AB plus I BA. But AB plus BA is equal to 0. So these are fermions. And you can check that if you have n pairs of these Majorana-Fermions, you can construct n fermions using this kind of trick. So the space of these two n Majorana-Fermions is exactly equivalent to the space of n standard fermions. Okay. So we define this operator, and now this is the Jordan-Wigner transformation. Let's also write the inverse transformation. Okay? So if you want to express the Pauli matrices in terms of the operator A, what do we have? You can check that this is transformation this one, sigma Lx is simply given by a product J from 1 to L minus 1 of I A to J. And then here you have this multiplied by A 12 minus 1. Sigma Ly is equal to the same string product J from 1 to L minus 1 of I A to J minus 1 A to L. Then you have sigma Z, which is I A to J minus 1. So given this, okay. How can you prove this? This is very simple, because sigma, a Pauli matrix squared, is equal to the identity. Okay? So it means that the inverse of this operator is the operator itself. So when you multiply by this operator, you find sigma x. So the only thing that you have to do is to realize how to write sigma z in terms of these two operators. Then, so you checking this is very simple. You just multiply the two of them, and what happens is that this string will cancel, and then you adjust sigma x, sigma y, and you know that sigma x, sigma y is I sigma z, and then you obtain the result. So this is the, you can easily check that this is the inverse transformation. Okay.
What did you say? That you multiply the two of them, so the sigma
By
part
this.
so it cancels, and
This cancels, so you have this one.
but no, okay.
This gives you sigma x, no? But then the problem is that this is an algebraic form, because then on the left hand side you,
Yeah, you have
you have sigma z.
Yeah. How do you do it?
What you do is that, okay, after, okay,
No, you can.
okay, no, okay,
Just say
after,
it.
okay, fine. Imagine you multiply it,
Yeah,
down you do the same here,
yeah,
down you use the sigma z is sigma x times sigma y.
exactly.
So you have to multiply the two,
Yeah,
and then what happens when you multiply the two, this term simplifies again.
yeah.
The only thing that it can do is to change the sign. But you want in this case, so it's fine. So it's just cancel. Just cancel, and then you can, in this way you determine sigma z, which is indeed the product of the two times and I. I due to the fact that sigma x, sigma y is I sigma z. Okay, that's
okay.
why this sigma
Okay.
sigma x, sigma y is I sigma z.
Oh yeah. Okay. Okay. Yes. Yes.
Okay.
That's,
So use this and then we find the data. So now you can apply this transformation to any spin 1/2 chain Hamiltonian, even if you have your favorite interacting model or even a non-integrable model, generic model, you can apply the transformation, and this will bring you the Hamiltonian to a fermionic Hamiltonian. Okay. But the convenience in this case is that when you apply the transformation, then the Hamiltonian is very simple. Yeah. Anyway, let's check what happens to these terms. Okay? So, all the terms. Now let's consider that. We have sigma z. Sigma z I already wrote what is that. So it's just two Majorana fermions. Sigma Lz is equal to I, A, J, A, J minus 1.
No, the A to L, right?
Oh, sorry, yes, you're right. L, L. Fine. Now let's consider the other term. Sigma x, sigma x. Sigma Lx, sigma L plus 1x. Now we use this transformation. Yeah. So we try sigma x is that thing. Okay. Remember, this is just sigma z. Again, so I can write. So sigma x, okay, it will be I a to j minus 1 times a to l minus 1 time itself, but now in the position l plus 1, so product j from 1 l, I a to j minus 1, a to l to l plus 1. Okay. Now, these are my Ramphelians anti-commute between each other. Okay. So this means that this a to j anti-commute with the a to l minus 1 as long as this index is different from this one. And in particular here you see that the sum is from 1 to l. So the first l minus 1 terms here, they just commute with this. And they go here and they cancel these terms. Because this, remember, they are just like sigma z. So sigma z squared is equal to 1. So you have almost all the terms here move there. And so you end up with, after this step, you end up with a to l minus 1. But here you must be careful because there is the lth term, which is that it doesn't commute. So you have, let's just write this term. You have a to l minus 2, a to l minus 1, and then here you have a to l plus 1. Now you see that this Majorana fermions here anti-commute with this because it's different. So it takes a minus sign when you move here. But when you move here, it simplifies this other a to l minus 1. Because we know that the a squared is equal to 1. It comes from that. So you have a l squared is equal to 1. And so when we anti-commute, you just take the minus sign. There minus I, a to l minus 2, a to l minus 1. Okay? Now you can convince yourself that you find something similar if here is y, or you put a y here. So you just change the indices here, but you will have always, the mapping will be always to a quadratic, the two Majorana fermions. What about the string of sigma z? Yeah. Why you have to put this string? The reason is here, in the presence of the string here. Because if you now detach the two operators, so let's consider now this again. Now, this is sigma x. Now let's assume that I move here by 1. Sigma l plus 2x. Then what happens here? I'll write the same again. So I will have this product, j from 1 to l minus 1 of I, a to j minus 1 times a to l minus 1. Then I have to put now this product up to l plus 1 here. Again, you have the L terms of this commute with a to l minus 1 because they are just different. They are okay. Each Majorana fermion anti-commute with this.
n minus 1?
You have L because you have L plus 1 terms.
Yes.
So you have L plus 1 minus 1 terms that commute, and only the terms correspond to L doesn't commute with this. So you can move everything to the left, not one term.
You take j equals to L, Then you have something like A to L, A to L minus
That is the
1.
term that doesn't commute. All the other terms commute.
Oh, I see.
Okay. So imagine you move this, all the other terms, but that, and then what do you obtain? L minus 1 term simplify. But then you have the term corresponding to L plus 1 here, which doesn't simplify. And so you end up with I, A, to L plus 2, A to L minus 1, then you have this, A to L minus 1, then here you have the term that doesn't commute, A to L, A to L minus 1, A to L, what is this, to L plus 3. Again, here you can move this.
It's 2n plus 1. The last term. Plus 1.
This term.
I think so. No. No, it's then.
So now this anti-commute. Again, so you and then it simplifies this term. So you take a minus sign from here. It becomes minus I, A 12 plus 2, A 12, what is this, 12 minus 1? This is A12, I was from here, okay. 12 plus 2 and A12 plus 1. Then A12, okay. Minus sign, 12 plus 1, and then you have A12 and A12 plus 3. So here you have a 4 minor Raphael instead of 2 for this term. So you detach sigma x, and then this is called an interacting term, if you want to treat it. So how can you simplify the Hamiltonian if you want? A way is to remove the term that create the problem here, which is to this term here with an I. You recognize that this is just given by sigma z. So you recognize that this is equal to sigma L plus 1z. And then so you write this as minus sigma plus 1z times A12 plus 3. So now this means that if you multiply this expression by sigma z, then you find something quadratic. And this is the reason why, the terms I show you, you have always this kind of string of sigma z in between the operators when you detach them.
Did you put 2 sigma z when you wrote the string? There were 2 sigma z.
Whenever, yes, but then you're right. There was a sigma z here and a sigma z here. But now the sigma z, what we did is that we moved this operator here.
No, yeah, okay, but when you wrote before the class of the Hamiltonians, you put 2 sigma z operators. In the middle of, okay, because you put sigma x L2 3.
Yes, in the case of sigma z.
Okay,
is
so
plus 2. And so you have just a single sigma z. If you consider the same with the plus 3, then you have to put 2 sigma z.
Okay. So you can go as far as you want to
exactly.
sigma z.
So now this is to show you. Okay, you can now you understand the procedure. So you can prove that for all the operators that I exhibit, the mapping bring them into a quadratic form, in 2 Fermats, 2 minor Fermats.
This is just some longer range hopping.
Yes, that's a weird long range hopping because you have this string of sigma z.
In the spin language, but the Majorana,
in the Majorana, this is interesting because in the spin language it's a very unusual interaction. But then when you consider the problem now in this free fermion model, then it's something that you can just consider a priori. There is some long range interaction. So you would put it, you would consider the term even from physical reasons. now, this is almost everything is fine. Now there is subtlety. And the subtlety is in the boundary conditions. Why? Okay, you have your transformation in your notes, so I will erase now then. Okay. I amend the chance. Now, let's imagine our Hamiltonian was something like this, so sum over L of some terms L. And now we want to focus on some spin chain with L sides, capital L sides. So L from 1 to capital L. Clearly we have to choose some boundary condition for the spins. Because what happens if you imagine, for example, to write the Ising model. For the Ising model, this is equal, again, minus J, sum over L, from 1 to capital L, sigma Lx, sigma L plus 1x, plus H, sigma Z. Now you see that when L is equal to capital L, here it appears as sigma capital L plus 1. So we have to make sense to this. Sigma capital L plus 1, because you have only L sides. So this corresponds to choose the boundary condition in your chain. And what I will consider here is periodic boundary conditions. Periodic boundary condition means that sigma L plus J, and here you can put whatever x, y, or z. This is by definition equal to sigma j alpha. Okay? So the Hamiltonian is translational invariant. It is periodic boundary condition.
Where J is just an index of the...
J is just an index J larger than 0, integer. Yeah.
Okay, it's not the chain. It's just L. Yeah.
Yeah.
Okay.
Okay. And yes, also we can also have larger than 0. You could be interested in different boundary conditions. For example, you can imagine also open boundary condition, or which correspond to choose. Okay, this is periodic boundary conditions. If you what we call in this context open boundary condition is generally when you say that sigma alpha L plus J is equal to 0. So you consider only the terms that are inside the chain. There is no interaction. So it's that if you open the chain, then you don't have an interaction between the first side and the last side. So if you have your chain in a circle, which corresponds to periodic boundary condition, and you start opening it, when you open it, then the interaction between this side and this side disappears. And this is why there is a node putting this 0.
Sorry. So what happens with our notion of locality with boundary conditions? When you say you have an operator that depends on L, that does make sense. Like if you put an operator between the last and the first side, right?
Yes.
And
This depends on the boundary condition, because if you put an operator here that has support here. Now, if you are considering periodic boundary condition, then this is a local operator. And now, if you consider the system with open boundary condition, then it's not local. So it depends on the boundary condition have an effect in the definition of locality when you are around the boundary of your system. Right? But as far as I can see now, the only problem is when you distinguish open from anything else, because open boundary remove just is cutting the chain, so it's putting the degrees of freedom very far away from each other. But still, okay, we say that this is more a matter of convention, because you could also imagine that here, when you have open boundary condition, you are just switching off the interaction, but the chain is still, the degrees of freedom are still close by. So it's your way of considering the system in a sense. So it's your choice. It depends on what you're doing, I think. Okay. Okay, so we focus on this. The solution of this problem with the open boundary condition, so they can be solved But you will, if you're interested and you start the calculation, you realize that it's more complicated. Yeah. Okay. So this is why I prefer to consider periodic boundary conditions. I just anticipate something and tell you that now let's assume that you are considering observables that are here, far away from the boundary condition. Then you should expect that the result will be independent of what you just said. Okay. So in other words, if you consider the system in the thermodynamic limit, then you won't see differences between open and periodic or whatever, anti-periodic, whatever boundary condition you can imagine. If you are here, if you are in the bulk of the system. Okay. So in a sense, choosing periodic boundary condition can be just a choice of convenience in some cases. Okay, so now we consider this, and then let's now see what happens when we apply this Jordan-Wigner transformation. Now, all the terms that are in the bulk, there is no problem there. Okay, so we can just do the calculation as we did before. But now let's consider, for example, here the last term, which is sigma Lx, sigma 1x. So you see that there is a difference, because when we prove the mapping to quadratic form, we use that the indices, the difference between the indices was equal to 1. Now, formally this becomes equal to capital L minus 1. So this is a very different operator with respect to the operator we considered before. So let's apply the Jordan-Wigner transformation, this operator. So you have product from J1 to capital L minus 1, and you have I, A to J, A to J minus 1, and then you have A to J to L minus 1. Then here the first operator is simply you have A, 1, 1. Yes?
Where sigma 0 starts on your chain?
Okay, this is okay, we have one condition. This is the side 1, and this is the side L.
Okay, and then your Jordan-Wigner string goes like this?
Exactly, because thanks for the comment. Because as you see, when I define the Jordan-Wigner transformation, there is a side which is privileged, side 1. So you have to choose a 1 in your chain. And generally the 1 is you choose the one that is close to the boundary. So here, if you imagine that here is the boundary, so you start counting from here, and it becomes capital L. Okay, this is a completely arbitrary choice. Okay, so we do that. But also, in our case of periodic boundary condition, it's really completely irrelevant. It could be more relevant if you consider open boundary condition, in principle. But in our case. So we consider now this term. You apply the Jordan-Wigner transformation, you immediately see that there is a big difference now. Because we have 2 capital L Majorana fermions instead of 2. Okay? But how can we rewrite this? Well, let's allow me to multiply twice for the identity. Okay? For identity, which is this one, this is equal to AI A to L A to L minus 1 squared. Remember, this is like sigma Z. So sigma Z squared is equal to 1. I'm not doing anything here. And then I write the same thing. Product J from 1 to capital L minus 1, I A to J minus 1, A to L minus 1, A1. I didn't do anything here. And now, you see, this is just the missing term in this product. Okay, this is why I multiply by this term. So what you find that this is equal to product from J, for J that goes from 1 to capital L of I, A to j, a to j minus 1. You have all the fermions here, Majorana fermions, multiplied by I, a to L, a to L minus 1, a to L minus 1, a1. Okay? This is equal to this. Okay, let's give a name to this. We can call it, for example, let's call it S. So this is equal to S. Now, I'm using that the square of the Majorana fermions is 1. So this is equal to I, A to L, A1. So, well, you now, a priori you don't see much different here. It's still not a quadratic operator. But there is a property of the operator S that makes this makes convenient to write the expression in this way. Because what you can prove, and it's really a one-line proof, is that this operator that I defined here, S, commutes with the Hamiltonian. Why? Observation. First of all, S squared is equal to 1. Okay? Second observation is that this is the product of all the Majorana fermions in your system. Your Hamiltonian is written in terms of an even number of Majorana fermions. Because it's an even number, every time that you try to commute these terms with this operator, you will find for each Majorana fermion, you will find always its counterpart here, itself actually. And so when you find itself, it just commutes instead of anti-commuting. Okay? But you have to do this twice. So this means that all the terms that can be written in terms of an even number of Majorana fermions will commute with an S. Okay, maybe this is easier to see in a spin language. I'm pretty sure that it's easier. So let's write what is S in terms of the Pauli matrices. Well, this is just sigma Z. So this is the product of all sigma Z in the chain. So this operator S is equal to product J from 1 to L of sigma J Z. Now remember all the terms of the Hamiltonian. You have the term which was sigma Z, and clearly sigma Z commutes with sigma Z. And then you have all the other terms have always a pair of X and Y, or Y and X. Again, X and Y, X doesn't commute with sigma Z, anti-commute. So you will get a minus sign when you find it. So if you consider a term like this, you consider S as XL as sigma L plus 1 Y. When you want to move sigma X on the left, you take a minus sign from here. So you have, this is equal to minus sigma Lx as sigma L plus 1 Y. Now you want to move this other operator, and again you take a minus sign, which simplifies this one. So this is equal to sigma Lx, sigma L plus 1 Y S. Okay. So all the terms that we wrote commute with this operator, if you want. So you can prove either in the Fagotti language or in the spin languages, in simple cases. Okay. So let's now write the what will become the Hamiltonian after the Jordan-Wiener transformation, take into account also the periodic boundary conditions. Okay? So also taking into account this operator S. You can, if you know, let's imagine that your Hamiltonian has also a longer range interaction. So it also connects the side capital L with sigma 2x. Let's imagine if you have sometimes like this, sigma 1z, sigma 2x. Then you can show again that the calculation is analogous. And again, if you will have something which is S, the result will be S multiplied by 2 fermions. Okay? So all the terms will be considered this property. Okay, so so what you find in the end is that after Jordan-Wiener transformation, if you have a periodic boundary condition in the Hamiltonian, you can rewrite the Hamiltonian in this form: 1 plus S divided by 2 times something which is quadratic, the minor fermions, H and then plus 1 minus S over 2. So here we are assuming that Hamiltonian H has periodic boundary conditions on the space. And okay, so
Sorry, just to follow, the S appears only from the boundary terms.
yes. So
Only
you
from
find
the
this-
1L.
Exactly. But and you can always bring the Hamiltonian this form.
In this
Now I
form,
will
depends on which Hamiltonian.
indeed. Now I will define this
Okay.
H plus and minus. But and moreover, indeed, if you consider open boundary conditions, I told you that it's more complicated. But there is at least a simplification. And the simplification is that you don't have this operator S with open boundary conditions. So the mapping is just to a quadratic form of fermions. But then you have other problems. So it's in the end. I think it's easier anyway just to consider periodic boundary conditions. Okay, I think I will give you now 5 minutes and then we continue. Okay.